Welcome, everybody. Today we're going to have a discussion on exploring quantum technology and the relation towards circularity, sustainability, and security. And this will be with Kelly Richdale from SandboxAQ and the World the World Economic Forum, and with Stephen Moore from the GSMA, being head of climate. So I'd like to start with you, Kelly. So quantum computing will bring massive power and massive ways to find new solutions. How does that link the massive compute to the sustainability agenda?
So I think if you think about quantum computing as a way to improve the ability to solve certain intractable problems, you can see that quantum computing has a huge potential to actually resolve some of today's sustainability issues. It can improve the use of electricity grids, optimize efficiency in electricity grids. It can predict better climate conditions and climate change. It can also be used for the creation of new materials. So if you think about it, it can create better batteries or render today's batteries more efficient in their use. It can be used to create new catalysts for green hydrogen production. It can be used to create new materials for solar power, etc. So that is on the one side. By solving some of today's fundamental and most intractable problems, it can really give a boost to sustainability in the environment. Now, having said that, let's just be clear that quantum computing today is still at an early phase. Companies are just beginning to show the quantum advantage. And by quantum advantage, we mean the point at which a quantum computer can perform better than any of today's classical CPUs or GPUs used in AI data centers. The question is, will a quantum computer itself be more efficient than today's CPU arrays for supercomputing or GPU arrays which run AI? And the answer is that there's been a number of studies. It's still early days, so the industry is still quite immature in this respect, and definitely more attention needs to be paid to the power consumption of quantum computers. But early study by players like OFEV show that a study taken in 2022 shows that a typical quantum computer will consume several magnitudes less than an equivalent classical computer, if we can call it that. Now, there are different quantum computing modalities. The ones that run at room temperature obviously have less power consumption. The ones like Pascal running on cold atoms or neutral atoms consume more because they need to be cooled. And then you have the superconducting qubits, which is one of the most prevalent modalities that are expected to show quantum advantage today. And the superconducting qubits consume more because of the cryogenic aspects. So the cryogenic cooling takes up a certain amount. It's basically the energy consumption comes from cryogenic cooling, lasers, and then the control electronics. So I think if you look at it, it still has the potential, even with the cryogenically cooled superconducting qubits, to consume less power than an equivalent supercomputer.
We've been looking ahead on what might happen regarding to quantum computing and how it can push technology forward, and it might also have an impact on everything we use today, meaning the equipment, mobile phones or whatever. It could have an impact. You just launched from the GSMA a report on the business case for reusing mobile phones. There is a push for new technology, all the time. So what do we do with the phones that we have left, and what can we learn from your report?
Yeah, thanks, Tieneke. So there's a huge number of phones actually that are sitting in people's drawers all around the world. So we estimate that there's between 5 and 10 billion mobile phones that are lying dormant, not being used. And in those phones, there's huge amounts of critical raw materials that we could be bringing back into the system. And obviously, if we can do that, then we avoid having to go out and mine new raw materials. So there is definitely a kind of security angle around this, because these are sitting within drawers in every country around the world. And effectively they are, if you like, kind of urban mines that we could be using to bring those materials back and even supporting domestic manufacturing as well. I think in terms of the business case for circularity, this is really around the fact that 80% of the environmental impact of a phone happens in its manufacture. This is because they're quite low energy to use. And this means that it's really important that phones are used for as long as possible. Because to make a new phone takes a huge amount of energy, raw materials, etc. So we see that, phones are valuable items, and we see that they are passed down or resold, and they do have second, third, fourth lifetimes. And particularly we've just done a very big consumer survey, more than 10,000 respondents across more than 30 countries. And it's clear actually in some more developing markets, there's obviously a very thriving informal marketplace for phones. Phones are also passed much more between family members and may have like fourth, fifth, sixth lives even. Because obviously it's less affordable to be able to buy a phone, which is obviously great for the circular economy because that's what we want to see. I think in terms of the challenge that we're seeing is that most of the market itself is still linear. So in general, phones are made, they're used, and they're discarded in some fashion. So either sitting in drawers or many of them still end up in landfill. So we're immediately losing all of those valuable raw materials. What we've seen from the industry in recent years is a response to this. So people are holding onto their phones for longer. I think we reached the fastest turnover back in 2015 when it was about 2 years on average that people held phones. We're actually now back up to over 3 years, pushing 3.5 years. And obviously we can see that the changes have really moved from the hardware of the phone. A lot of phones now all look very similar. And the difference really lies in the software. And we've seen like big developers in software. And really when you use your phone, you're not really interacting with the hardware so much. You're choosing which app in your phone that you want to use. So this is helpful for the circular economy.
So it's, I think, very good news that we keep on to our things much longer than we did before. However, imagine that we have some kind of leap step forward with quantum. What could be potential risk on basically using mobile phones, using our networks? So what is the risk if quantum computing is there from a security perspective?
So the upside of quantum computers is they solve intractable problems. The downside of quantum computers is they have also the potential, once the hardware is ready and able to run what's called a cryptographically relevant quantum computer, is that they can also solve intractable problems. And much of today's trust infrastructure is based on cryptography. And the typical public key cryptography or public key infrastructure will be broken, will be rendered vulnerable by something called Shor's algorithm. So the quantum algorithm already exists. It's just waiting for a quantum computer powerful enough to run it with sufficient error correction to actually run it. So acknowledging these challenges, the National Institute of Standards and Technology, NIST in the US, so a group of governments came together, about 60 countries came together to bring out and standardize a new set of what are called post-quantum cryptographic algorithms, more correctly called quantum-resistant algorithms that will be resistant to this well-known quantum attack. And that is actually something which they were standardized last year, in the middle of last year, and they're now being implemented in telecoms and in governments. The leading regulation is being mandated by the United States, which has mandated that its agencies, federal agencies, are required to move critical infrastructure applications and the crown jewels of data to post-quantum algorithms by 2030, and everything by 2035. So the path to migration is really tight. A lot of companies, including telecoms, are trying to figure out where their cryptography actually lies. So the first stage is something which SandboxAQ does, is to perform a cryptographic inventory, which is to understand where your cryptographic bill of materials is, a bit like a software bill of materials, to understand in your supply chain which are the vulnerable areas and which cryptography is used that could then be vulnerable to a quantum computing attack. Not even a quantum computing attack, just simply improving your cryptographic and trust stance and cryptographic resilience.
So that's quite, astonishing. So the United States declares that they have to be post-quantum ready or quantum secure ready by 2030. So that's basically tomorrow. From the GSMA, is that also something you look into? How do you collect and get people together to raise this awareness? And what do you foresee that will happen? What will be the impact on network infrastructure, on data centers? So what's the vision of the GSMA on this?
Yes, I mean, it's something that we're constantly horizon scanning to look and understand what big new thing is going to be coming down the line that's going to affect, for example, the amount of energy we use across the industry. So AI obviously being a big part of that. Quantum computing may be, as we heard from Kelly, it could be a friend, it could be a foe in that respect. And then obviously the material side of things as well. If we're going to have to suddenly switch over to quantum computing, therefore, we're going to have to remove a huge amount of existing infrastructure. That's going to be a significant amount of waste potentially. So I think we definitely need to reframe that to think of what we're taking out as being valuable, to being material rather than waste. I think it's helpful to have a timeline really, because we know how much network infrastructure is already out there. And if we have a timeline for when we need to move from one over to the next.
Kelly, we have about 5 more years to be quantum ready.
Yes.
So
assuming that we stick to that timeline and, and whether that's required in a US context, whether that's also required in other countries as well, then yes, I mean, that's helpful because what we've seen actually with the kind of third sector of refurbishers and recyclers, they've really stepped up over recent years because, as I say, many phones, the phones are needing to be recycled, refurbished, reused. And we've seen that we've got increasing numbers of processing facilities able to do that. But what we also are told from these recyclers, refurbishers is they need scale. Like they need a sufficient number of devices coming back in to meet, the kind of economies of scale in order to make it cost effective. If we're going to have a significant amount of network infrastructure coming out, then obviously that's going to provide the scale, and it's going to provide actually quite a good business case for those recyclers, refurbishers, dismantlers to actually take that equipment, dismantle it, and then put it to some good use elsewhere.
So we've seen that the subject like the circular economy and reusing equipment and dealing with the critical raw materials is a very complex thing. How can we already step up today? And what is the GSMA doing very concretely, maybe in 1 or 2 points, to make sure that the situation we now have of mobile phones where we had to learn how to reuse them, can we step up and do that quicker for data center hardware and for network equipment? What can we speed up?
Yeah, I mean, one of the things that we've actually just launched last year was a second-hand equipment marketplace, a network equipment marketplace. So, I mean, I think this is really helpful for ensuring that we don't lose equipment when perhaps it becomes obsolete in one jurisdiction or one country, say the US. Maybe we can remove it and make it be used in another area. So the network equipment marketplace really, we've had, I think, maybe 50 mobile network operators already signed up to use this, and it's a matchmaking. So it's somebody has some equipment that they're taking out of their network, they put it on there, and they find somebody who needs it for their network. We're also looking at whether there's more that we could do on the devices side as well. So I think tracking devices over their lifetime is something that we still don't do very well. So we don't really know actually where a lot of devices end up. However, we do run a TAC database, an IMEI number database from the GSMA, which is used to understand if a phone has been stolen. So if it comes on the market, like a provider can check if a phone has been stolen. So we see there are potentially opportunities to use that database to support understanding what happens to phones, maybe how it's refurbished, how long its lifetime is, and that's something that's useful for us to measure so that we can extend the lifetime of these devices. I think there'll be even more that we can think about, related to this, related to the changes that will have to be made with data center hardware as well. It sounds like there's going to be huge opportunities to bring this equipment, recycle it, put it to better use as well.
Right? Yes, you like to respond.
So I think the question of recycling equipment and what legacy equipment will still be relevant is absolutely critical as we look at the different compute modalities coming out. If we taking a step back again to the post-quantum cryptography, the algorithms that are being used, the cryptographic algorithms, are longer and require more processing, have higher processing requirements than and higher memory requirements than today's cryptography, which definitely poses a challenge for the legacy hardware. Are they powerful enough to run the PQC algorithms? So that's point number one. Secondly, it's interesting to see whether the advent of GPUs is rendering redundant CPUs, and whether QPUs, quantum processing units, will render GPUs and CPUs redundant. The jury is still out on that, but what we can see is, and the belief is, that the future of compute high performance compute and omni-compute will run on hybrid infrastructure. So we're not going to get rid of all the CPUs. I mean, we use a standard computer running on a computer processing unit to interface with humans. We will still have AI algorithms probably running on these GPUs that are being delivered by companies like NVIDIA. And QPUs will run specific subroutines that quantum computers do better than other compute modalities. So we're expecting there to be a huge increase in compute, but running on hybrid infrastructures, CPUs, GPUs, and QPUs. Now, the question is, at what point will QPUs potentially render legacy equipment unusable, and how that will be recycled? But you brought up a very good point earlier, is the Javelin paradox. To what extent will our energy and our compute requirements simply increase to such an extent that we use everything, that we will use all of the compute modalities and still require more? And if we look at some of the problems that are being solved by these future hybrid infrastructures, it's almost unlimited in its application to today's world. So,
thank you very much. I think that's a very important point. And maybe to drive to the last question, both quantum and sustainability, they require a financial investment. But what is needed to drive the quantum, responsible quantum technology? How do we make it responsible from an inclusiveness perspective, but also from a circularity perspective? So maybe as a last question.
So in my role at the World Economic Forum, SandboxAQ and the forum, we wrote together with IBM a report on the quantum economy blueprint. And it basically talked about how countries, particularly in the global south, how they could enter the quantum economy, because the digital divide is significant, the AI divide even bigger, and the quantum divide will be huge. And within that context, we talked about the different building blocks, and responsible quantum is absolutely one of them. So if we're looking at responsible quantum and sustainable quantum, how do you sustainably build quantum computers? And then how can quantum computers contribute towards sustainability? We touched on that a bit earlier in the discussion. There is a critical aspect, however, which is access. Because what we see is that the building of a quantum computer is highly monopolistic. It requires a huge amount of capital input, and these will not be built easily by SMEs or by smaller countries. So how can we ensure that the global south is not disenfranchised? Because quantum computers are so powerful, we need to ensure that they have adequate access controls. And they're talking about, if you look at the financial model of KYC, know your customer, in the world of quantum computing, we're talking potentially about KY3C, know your customer, content, and cloud. But are we ensuring that the global majority have access to the benefits of quantum? And that is a huge issue, as we see quantum and AI becoming part of a kind of digital arms race in today's geopolitical tensions.
So that's, I think, quite also a warning and an awareness about what could happen and where we could look out for to make this, ethically and inclusive. On a final note to you, Stephen, how can you push this in the direction that is beneficial for all? And what's the role of the GSMA in this?
Yeah, so I think thinking about it from a sustainability aspect and thinking particularly about what the environmental impacts of this could be. So it's something that's being very much considered with the development of 6G. So obviously we rolled out 5G, we're thinking about 6G, and a lot of the discussions around 6G at the moment are around what is the environmental impact of it going to be? What is the environmental impact of this new generation of equipment going to be? So energy efficiency is really at the heart of that, because for network equipment, it's really about how energy efficient it is to run. But it's not just that, it's also about the materials that go into making it and thinking about, can we use recycled content? How much recycled content can we see? We're already seeing that being used in phones. So Apple, for example, is publishing each year the increasing levels of recycled content they have in their phones. They have also made commitments to use renewable energy to manufacture their phones. So obviously this reduces the embodied carbon within what you produce. So it's thinking about renewable energy, it's thinking about recycled content, and it's thinking about how exactly it's going to be used, and making sure that you are embedding energy efficiency principles at the heart, which is something that will happen with 6G and hopefully something that will be very much part of quantum computing as well.
And what is it from a climate perspective that you're most optimistic about for 2025?
Well, as you mentioned, we've launched this big circularity report, the business case for circularity, and we asked one of the panelists on the launch session that we did yesterday, what would you like to see here at MWC by this time next year? And they said really for this to not be a kind of niche topic, but just to become BAU. And this is what we've seen with kind of previous topics. You know, it's on the sidelines, but then suddenly it's right in the middle and everyone's kind of almost take it for granted that it's part of business as usual. And we think that that's going to be, we think the topic of circularity and the topic of kind of recycling of materials is just going to start to be talked about as BAU in the years to come.
Yes. And in 2025, we expect significant contributions from a combination of AI and quantum inspired algorithms, if you like, towards clean energy production and new materials that are less polluting of the planet. So here's looking at technology progress contributing towards sustainability.
Be able to find this?
So you can already see huge leaps in battery efficiency and new materials for batteries. SandboxAQ does that, for example, using AI quantum chemistry algorithms running on AI GPU arrays, for example. You don't need to wait for quantum computing to use quantum chemistry to improve today's new material production. And so if we look at the development of new catalysts for hydrogen, better, new efficient battery materials, new plastics that are not polluting, even the ability to break down forever chemicals like PFAS, all of that is used today in this combination of quantum chemistry, knowledge about quantum chemistry, but using AI GPU arrays to run those algorithms. And those are already making significant contributions today.
Well, I think that's the knot for rounding it up for today on an optimistic note about the possibilities and what it can bring, and also with the guidance of the GSMA. So hopefully next year more on the quantum computer and circularity and sustainability. I'd like to thank you very much for this very interesting talk. Okay, thank you.